Good evening. And tonight we're taking a look at ionization energy and electron affinity. So just as we did before, it's important that you take a look and are comfortable with the terminology that we're working with today. So yesterday we looked at nuclear charge, electron shielding, and atomic radius, and those first two especially are going to come back in a big way today. So take a minute to look those over if you need to. Today, then, we're going to look at ionization energy, often abbreviated IE, which is the amount of energy needed to remove an electron from an atom to create a cation. So you guys have to remember from a few chapters ago, a cation is a positively charged ion. Why is it positively charged? Because it lost a negatively charged electron. So the amount of energy it requires to do that is the ionization energy. And then kind of the opposite of ionization energy, we have electron affinities, again abbreviated EA. And this is a measure of how much energy is released when an electron is added to an atom to make it an anion. So the opposite of cations are anions. These are atoms that, well, they're not atoms, they're ions, that have added electrons, they have more electrons. So electron affinities are measuring how much energy it takes to add an electron to an atom. Now let's start with our IE, ionization energy. So here is an image here. We're removing an electron from an atom. And the question is it a lot of energy required? Or is it just a little bit of energy required? How much energy is required to knock that electron off? It's going to depend on three things. So nuclear charge, electron shielding, and kind of new here, how crowded the orbital is. We'll take a look at all three of those things on the next slide here. So as you move down a group, doesn't matter which group you are, you can pick whatever group you have, the ionization energy always decreases. So as you're moving down a group, look at those numbers, they're getting smaller every atom as you move down. The reason for this? Increased shielding. So here's lithium, not very many electrons, inner shell electrons, between the valence electron right here and the nucleus. So that attraction between the nucleus and that outer electron, that valence electron, is going to be really strong. It's going to be like trying to pull two very strong magnets apart. We move down one level in the group. Here's sodium, and look at that. Now we've got more shielding going on. We have 10 electrons in between that valence electron that we're trying to remove and the nucleus. So the nucleus, the attraction between the nucleus and that electron is not nearly as great on sodium as it is for lithium. And we see that here. It takes less energy to remove that electron from sodium than it does from lithium because of that shielding. As you move across a period on the periodic table, in general, the ionization energy increases. And this is due to nuclear charge. So remember, nuclear charge is how many protons the atom has. Lithium only has 3 protons. Neon has 10 protons. 10 positive charges are going to hold on to electrons a lot stronger than just 3. So that's a nuclear charge, and that's why, generally speaking, the ionization energies go up as you move across the periodic table. You're adding electrons. Lithium only has 3, you're adding protons. Beryllium has 4 protons, so 4 protons hold on stronger than 3. Boron has 5 protons. 5 is going to hold on stronger than 4, stronger than 3. There are a few breaks in this pattern to be aware of. So you might have noticed first break is beryllium with 899 and boron with 800. So that's our break between the group 2A and 3A atoms here. The decrease is due to the fact that once you get to boron, here's boron, we have kind of that extra electron in the 2p. That 2p is a little bit further out from the nucleus, than the 2s. So here's beryllium. He's got his full 2s there. And here's that extra electron that boron has. That extra electron is in the 2p. It's not going to be as hard to take this electron because it's a little bit further from the nucleus. This electron here from beryllium, on the other hand, this electron is going to be closer to the nucleus. A 2s is closer to the nucleus than a 2p. So that goes for all of the 2a and 3a elements. You'll notice we go down from the magnesium to aluminum. Ionization energy goes down. From calcium to germanium, that ionization energy goes down. Again, big reason for that is that that p orbital, whether it's a 2p or a 3p or a 4p, that p orbital is a little bit further away from the nucleus than the s. The next one to notice the trend on is between 5a, the nitrogen family, and 6a, that's the oxygen family. So again, you notice the decrease, and you can really see it on the graph here. Going up, we're going up, we're going up, and then we go down. The reason for that is because of space in the p orbitals. Anyone in that p3, the 5a family, they all have a p3, which means they have one electron in each of their 3 p orbitals. You can see that here with orbital notation. When you go to the 6a group, that's the oxygen family, they all have that extra electron paired up. See, it isn't here up here. That extra electron is going to be easier to take. Again, we're talking about that red electron, that red arrow. It's going to be easier to take because it's crowded in these p orbitals. It's the same amount of space in this p orbital as in this one, but we have more electrons. We have 4 electrons in these orbitals and only 3 here. So these electrons, again, I know they're spinning in opposite directions. That does definitely help them to coexist, but they're still negatively charged. They're still pushing each other away, and so that makes it a lot easier to take this red electron as opposed to any of these black electrons. And that's why we see, again, the fall in electronegativities from group 5a to group 6a. It goes down because it's going to be easier to take that electron there. Once you reach the 7a group and eventually the 8a group, the nuclear charge has increased. It's a lot higher, so it's going to be a lot more difficult. We're back on track with a much larger ionization energy to take those electrons. Those protons are going to hold on to them a lot harder. All right, next up we'll take a look at electron affinity. So affinity means love. So electron affinity is a measure of how much energy is released when an electron is added to an atom. So how much do atoms love to gain electrons? You'll notice that the numbers here are negative values. They're all negative values. This represents how much energy is released when an electron settles into its orbit. So the energy is coming out, so that's why it's a negative value. The larger that value, the more energy is released when the electron is gained. So more energy being released means a greater electron affinity. And that means the atom really likes to gain those electrons. In general, electron affinities decrease down a group. So again, as you look at those groups, we see our values going down the group. This is due to increased shielding by inner electrons. So inner electrons are shielding the nucleus, and so that makes it so that there's not as much energy, there's not as much relaxation when that electron joins. The nucleus is not as attracted to those valence electrons being added. An exception you'll see are the 2p. Here's the 2p, boron, carbon, nitrogen, oxygen, and fluorine. Notice they actually go up a little bit. And the reason for this is that the 2p is a pretty small orbital. If you add electrons to any one in the 2p, any of these atoms here, you're kind of running out of room. You're squishing them together, and therefore there's some repulsion between these electrons. By the time you get to the 3p, that's the aluminum, silicon, phosphorus, sulfur, the 3p is a little bit larger orbital. There's more room for those negatively charged electrons, and therefore there's more relaxation, more energy released when an electron joins one of those atoms. All right, how about as we move across a period? Well, hard to say that there is one trend. Yes, it's definitely going up, but look, it starts high, goes low, goes higher, goes low, goes higher, goes low. So it goes very high, goes really low. So it's tough to say that there is one particular trend when we move across a period. Instead, when you're looking at electron affinity across a period, you really have to analyze each element individually. Let's start off by taking a look at lithium. Here is lithium right here. So lithium has, currently, it has one electron in its 2s orbital. When you add one more electron, again, that's what electron affinity is, we're adding another electron, you go from 2s1 to 2s2. And that's okay. Lithium has a reasonable EA, kind of wants an electron. It's okay to add an electron because you're only going from 2s1 to 2s2. On the other hand, we come down here to beryllium. Look at that, pretty much zero electron affinity. Beryllium does not want an electron at all, pretty much will not take an electron. And the reason for that is that he already has his 2 electrons in the 2s. He's got 2s2, he's like this, he's filled up. So if you're going to add another electron, you'd have to open up the 2p. Opening up another energy level, well, not necessarily an energy level, but opening up another orbital, that takes a lot of energy. It's hard to do that, so beryllium basically has no electron affinity. Another example, carbon. Carbon's really high, one of the highest electron affinities. Again, the reason why is that carbon has an empty p orbital. He has 2 up arrows in that empty p orbital. So adding an electron really does very little to disrupt carbon. It gives carbon 3 up arrows, plenty of room, no problems for carbon. Then we see that huge drop down to nitrogen. And again, the reason is that nitrogen has an up arrow, has an electron in each of the 3p orbitals. If you're going to add another electron, again, think about it. That's what electron affinity is, adding another electron. If you're going to add another electron to nitrogen, you'd have to start pairing up electrons. You have all 3 of your up arrows. Now you have to start putting the down arrows. There's going to be repulsion there. I know they're spinning in opposite directions, but there's going to be repulsion there, and that leaves nitrogen with very little electron affinity. Halogens, that's fluorine, chlorine, and bromine. They have a gigantic, you can see they have the highest electron affinities, and that's because they have that empty spot. They can hold one more electron. On the other hand, noble gases, helium, neon, argon, krypton, they have the lowest electron affinities. They're down at the bottom, all of them. The reason for that, they have a full outer shell. They're completely filled up, a full octet. If you're to add another electron to neon, or argon, or krypton, or any other noble gas, you'd have to start a whole new energy level. From neon, you'd have to go to the 3rd energy level. His 2nd is all filled up. From argon, you'd have to go to the 4th energy level. His 3rd is filled up. That's very difficult to do. A lot of energy required in opening up one of those new energy levels. Therefore, noble gases have 0 electron affinity. They do not want to add an electron. It's going to cost them a lot of energy to open up that new energy level. All right, thanks for joining me. And again, pay attention to those terms. Ionization energy versus electron affinity are the ones we talked about today. I'll see you tomorrow for our next lesson.